So good afternoon, everyone. Welcome to our August NITheCS Mini-School. My name is Francesco Petruccione, and this afternoon we have the pleasure to welcoming a team that already delivered a very successful mini-school last year with a very nice dialogue format, and I'm sure they will repeat the same format today. So let me, for those of you that might not have met Professor Janelidze and Professor Goswami, let me briefly introduce them to you. Amartya studied did his MSc in Calcutta and his PhD at the University of KwaZulu-Natal in Durban. And before joining the University of Johannesburg, where he is at the moment, he spent some time at the University of Zululand and at the University of Limpopo. And as I mentioned, last year, together with Professor Janelidze, he delivered the mini-school on an introduction to category theory. Yeah, Professor Janelidze is based at the University of Stellenbosch since 2009, and he leads there the undergraduate program in mathematical sciences and also coordinates the modules about foundation of abstract mathematics. Yeah. And he also serves on the editorial boards of various international mathematics journals, and he's at the moment the president of the South African Mathematical Society. Yeah, so we are very lucky to have this very qualified team to introduce us to set theory. Yeah. Zurab and Amartya, I see you already sharing the screen, so you're most welcome to start with your presentation. And to the participants, please make use of the Q&A or raise your hand, and we will give you the right to ask the questions in person. So thank you very much, Amartya and Zurab, for offering this very interesting course. And please, the floor is all yours.
Thank you very much, Francesco. Thank you for these introductions. Yes, it will be almost in the same approach what we have last year with respect to this introduction to category theory. And it will be absolutely informal with respect to the style of the presentation. So please feel free to interrupt at any moment, ask your questions, please join in our discussions. So it is a friendly conversations between two people. And just to try to understand the relevance of this theory with respect to mathematics and some applications in other areas. Zurab? Your microphone is muted.
Thank you. It's exciting once again to have this chance of presenting a mini-school. Set theory. Why set theory? Because of the universality of the language. And maybe one should begin with a kind of philosophical beginning. If we want to have a formal language which enables us to make absolutely precise every single scientific idea we have, that language is set theory. And that language was developed at the end of 19th century, beginning of 20th century. And it was the first fully functional formal language that could encode all of mathematics within it. And in this mini-school, we will present some aspects of it which you might not have seen. You might have used the language of set theory a lot in your work, but you might not have seen its foundations, what's happening behind the stage. Okay, so where shall we begin, Amartya?
Okay, first question is everything appearing in mathematics is a set?
Yeah, so that is the hypothesis of set theory. So set theoretic perspective on mathematics, or the universe in general is that everything is a set. And there are also various different kinds of set theories. So the one we are presenting here is the one that was formalized for the first time by Zermelo. So the axioms we will look at will be Zermelo's axiom. And from that point of view, everything is a set. And this conglomerate of everything is usually called universe of sets. And we use the term universe because indeed it has this power of expressing all phenomena within it, all precise phenomena within it. So we can draw it like this. We have a universe where instead of stars, we have sets. And there could be many different universes of sets, you see. So it's not that it's supposed to be one. And we will be studying an abstract universe of sets, which can be, such a study can be used for any specific one later will indulge in.
Right.
So
but
yeah,
there should be
also,
So then why we should bother about these certain axioms to set up this theory to get something new?
Okay, so what we're seeing here, each of these pictures, this 4 regions I drew, right? So each of these pictures are supposed to be representing the universes inside which we can encode all mathematical phenomena. Now, just like with any mathematical structure, there is some information that the structure comes with. And then we want some basic facts that we can utilize in computation or description and so on. So these basic facts are called axioms. Now, the information that the universe of sets comes with is basically data of, for each set, right? We need to know how does it decompose into more basic sets, which are called elements of the set. So intuitively, what is a set? A set is an object that has elements. And we can draw it on the picture like this. For instance, this drawing will now mean that X is a set, and A, B, C are its elements.
So
that means are sets too. Sorry?
So that means at the very beginning we are assuming we have at least one set which exists. Otherwise, we cannot start this discussion, right?
Well, we could potentially have an empty universe where there is nothing.
Yeah. But that will not be quite interesting to build such a theory.
Maybe not. But within a universe of sets, we actually do want to have something called the empty set. And that's the one that does not decompose into any further elements. So if I look at its decomposition of elements, it is just an empty space.
Right.
Now, the thing is that these pictures I'm drawing, we can actually encode this entire structure as a directed graph, just like the directed graphs we used to start category theory with last year.
Right, last year.
So in this case, for example, I could represent this information of what is element of what by arrows. I could have an arrow from A to X, meaning that A is an element of X. I could have an arrow going from B to X as well and C to X as well. And in this arrow notation, to convert from the arrow notation to the bag notation, it's quite easy. You have your set X, and then you collect in the bag all the other sets which have arrows going to X.
So you wanted to mean that to differentiate between this notion of a set and the elements of a set, we need to introduce this notion of arrow.
Yeah. So arrow is kind of the relationship between sets. So the relationship that is given as a data on our universe of sets. So we will write this like this, A and this element symbol X, which is obviously familiar to probably everyone attending here. That could just, so purely purely formally speaking, basically what I'm saying here is that we can think of a universe of sets as a directed graph, where there's only one directed arrow between any two, if there is at all. So that you cannot have two parallel directed arrows. Huh? So it's just a directed graph, and when there is an arrow from A to X, then we write this way and say that A is an element of X.
Right.
But of course, A itself might have further elements, so that there might be something else that's an element of A. Let's say D, and so on. And in the end, we're going to get very interesting hierarchical structures. Like, for example, we can begin, in fact, we can begin with nothing. We can begin with the empty set. So that one has no elements. And
so that means there is no arrow going to it.
That's right. That would mean that in the given universe, there is no arrow going to this object. Right. And then we could have a set whose element this one is, and that's the only element of that set. And then if that's the only element of that set, we will write it this way. Now this curly brackets indicates to you that we are describing the elements of a certain set, and whatever goes in between curly brackets should be the list of all the elements.
Yeah, you mentioned about this empty set. Can we have more than one empty set in our universe?
Well, in the beginning, yes. Before we impose any axioms, you can have as many empty sets as you like.
Okay.
So I've just constructed another set now, and maybe a third one, which will now combine the previous element with maybe the empty set. So now this set has two elements. One is that, and the other one is that. But now looking at this picture, you see that we get a kind of complicated picture, which is kind of spelling out all the elements of all the elements of all the elements of this set, right? So it has two elements, this one and that one, but that one has a further element, that one, and so on.
So when you mentioned one element, two element, three elements, that means our usual notion of this natural number, we can actually construct, starts having this idea of these empty sets and these new sets from it.
Well, yeah. So I mean, the whole idea is that we should be able to encode any mathematical concept in the context of a universe of sets. And now you're basically asking, let's see how we can encode natural numbers.
Yes.
And I'm going to answer this question in the style of von Neumann, who gave a nice way of encoding natural numbers as sets. So von Neumann's approach is to take number 0 to be the empty set.
Yes.
And number 1 is the set whose element is the empty set. In other words, is the set with 0 as the element. Number 2 is the set whose elements are 0 and 1. So each time you have as many elements in the set as the number you're defining, and so on. So this shows you how you can define numbers inside the universe of sets. Of course, you need to have a universe in which these constructions are possible.
Yes, of course, of course. And this actually gives another way that sometimes when we talk about natural numbers, some people say we should start from 1, or some people say we start from 0. But from the construction point of view, it is natural to start from 0 because that's how you get this empty set.
Yeah, so it's kind of this beautiful thing about set theory that you can basically begin with nothing, right?
Yeah.
You create a set out of it, that's the empty set. And then you can use that to construct all the other mathematical objects from it.
All the mathematics, yes.
Yeah, so it's kind of creating everything out of nothing, just like
out of
the Bible. We have some questions on Q&A. Let's try to answer.
Yeah,
these.
let's see.
Circularly linked sets possible? So yes, they are possible before we introduce any axioms. So at the moment, so far in the lecture, we haven't introduced any axioms, so anything is possible. So here is an example of a circular situation where you have, let's say, 4 sets, A, B, C, D, and they are each other's elements in the way it's shown in the diagram. So this is allowed because we haven't imposed any restrictions yet on what a universe of sets can be.
Yes, absolutely. There is another question.
And yeah, is it not true that some truths are impossible to prove? Does this not make it impossible for an axiomatic system to encapsulate everything? Yeah, it's a very good question. So yeah, so it turns out from Gödel's theorems about incompleteness that in the theory of sets, no matter how many axioms you introduce, you will always have some properties which can neither be concluded nor its opposite can be concluded. So more axioms available to impose if you want to.
Yes.
The next question asks, does not having any axioms imply you can do anything, or doesn't it actually imply you can do anything? No, in fact, the fewer axioms we have, the less we can do, because then we don't know what we can do. The axioms will guarantee us that we can do certain things. And maybe it's worth mentioning what these axioms are, but before we even mention the axioms, maybe we first do something, we repeat the historical mistake. So you could formulate the following axiom, which we will later explain why this axiom is invalid, but you could formulate that the axiom saying that any collection of sets is a set. So what does that mean? So if I'm given a universe of sets, right? Now I'm saying that no matter which bag of sets I identify, right? And now I want to find a set whose elements are exactly these. Does it exist? Exactly the ones that I circled. So for example, if this is called A, B, C, D, E, these are my sets. I want to find a set F whose elements will be exactly A, B, C, D, E.
Do you want it to mean that can we always describe sets in terms of properties?
Well, not going into properties yet. Here I have a picture, right, of a universe of sets, and I just randomly picked some collection of sets in there. And I'm wondering if my universe, I will be able to find an F whose elements are these sets and exactly these. And maybe I can find such F, the one that decomposes into this. And so the axiom tells me that I should always be able to find such F. So any collection always gives rise to a set. That's what it says. So that will be one axiom. And the other axiom I might want to impose as well is that sets are uniquely determined by their elements. So if two sets have the same elements, then they are equal. And of course, this will exclude the possibility of having many infinite sets. Many empty sets.
Empty sets, yes.
Yeah. So there's nothing wrong with this. Yeah. Sorry, yeah.
Yeah. In this first axiom, when you say the collection, will it not be a cyclic way if we wanted to understand what does it mean by collection again?
No, we are kind of trying to pretend that we have a very concrete objects on our table, which we call sets. And it's not a formal discussion. It's intuitively saying that.
Right.
Of course, if we want a formal discussion, first we need to set up a formal language, and we are actually setting up a formal language in which we can formalize everything. So one has to start from somewhere which is a bit less formal before you can move to the formal story.
Build such thing, yes.
But it turns out that this axiom, which actually has a name, it's called comprehension, is wrong. So it turns out that it's not possible to have a directed graph having this feature that no matter what points you identify in it, you will always have another point such that the things you've identified are exactly those things that have an error going into them. And there is a well-known, I mean, this is called Russell's paradox.
Russell paradox, yes.
And I can now demonstrate this is wrong. Well, look, you see, if there were finitely many elements in my universe, right? I mean, if there are finitely many sets altogether. So let's call this universe something. Let's call this universe U, right? This U is not a set itself. It's just the collection of all the sets I'm considering.
Oh, that's it. Yes, yes.
If the size of U is, let's say, n, right? So if there are n many objects in U, right? Then the number of collections of sets will be 2 to the power n, right?
Right.
So if I'm trying to isolate a collection, for each element I have to decide whether it belongs or not to the collection. So for each object I have 2 choices, and then I have to make this 1 or 2 choices for every element in the universe. So that's n many choices of 2, and so it gets to be 2 to the power n. So if it was possible to express every collection as a set, right, then it would mean that 2 to the power n is less or equal to n. If it was possible to fit every collection as a set on its own.
Right.
But the thing is that this is never true. Even when n is 0, it's not true. So this is never true. So if a universe is finite, quite clearly the axiom of comprehension fails. But what if the universe is infinite? Because infinite sets have very weird behavior. And here is an example. I mean, you might think that there are more integers than there are natural numbers, simply because integers are all the natural numbers plus the negative numbers, right?
Right.
So you might think that there are more of integers, but actually there's the same number of them, because I can pair them like this. I can have a one-to-one correspondence between all the integers and just the positive ones. It shows that the size. So infinite. When it comes to infinite things, things can get weird. So maybe
very weird. Yeah.
Yeah. So maybe when U is an infinite set, it is possible to make this axiom fulfilled, because of the weird behavior of infinite sets. But it turns out that infinity is not that weird. It turns out that even in the infinite case, this axiom will fail. And to prove that it will fail, we will construct a collection of sets for which we will prove it can't be a set. So, and this is how it's done. This is a very famous thing which is all over the internet in very different forms. So let's consider the collection of those x's in my universe. So x represents a set here, such that this is true.
X is not there.
And let's call this thing y.
Yes.
Okay, what am I saying here? So I've got this universe of sets, right? And I'm isolating all those dots which do not have an arrow looping onto itself. Remember, this would mean that there is an arrow from x to x, right? And now I'm saying this is not true. So there can't be arrow from x to x. And these are the x's that I'm going to pick out as my collection. So all the ones that have the loops, I'm not going to select, but all the ones that don't have looping arrows onto itself, I'm going to select. And now I'm going to prove that this collection cannot have a representing set.
That means this y itself is not a set.
Yeah, so they cannot exist in the universe. We cannot find, no matter what the universe is. It's a very abstract proof. No matter what the universe is, we will never be able to find a Y whose elements are precisely the ones I picked here.
Mm.
So this notation, by the way, means that we are selecting these objects that satisfy this extra condition.
This property, yes.
So why is it impossible for Y to exist? Well, if it exists, right? Let's assume it exists. And we ask the question, is Y an element of itself, right? Does Y itself have an arrow looping into it? If Y has an arrow looping into it, right? Remember here we selected all the ones that don't have arrow looping into it. So if Y has an arrow looping into it, what will happen, Amartya?
It cannot satisfy that property, so it shouldn't be there.
Yeah, so if Y has an arrow looping into it, it can't be among those that we selected because we selected
Right.
those. So therefore we can say that this is not the case, right?
Right, right.
Okay, but on the other hand, if Y does not have arrow looping into it, so let's say...
Then it should be there.
Yeah. That if there is no looping arrow, then Y must be one of these things in a collection, right?
Yeah, because that is the condition how we defined Y.
Yeah, so then it must have been selected, so then Y must be in Y. And now we get a very fascinating equivalence here that being in Y is equivalent to not being in Y. But this is impossible because if one of them is true, the other one will be false, and truth and false cannot be equivalent to each other.
Yeah. Because
And
first
why
one
did
is
we
saying
come-
that, yeah. The
Yeah,
first one
and
is
so-
saying that we have an arrow, but the second one is saying we do not have an arrow.
Yeah, exactly. Yeah.
Yeah.
So we came to this contradiction by assuming that such set Y exists, therefore Y cannot exist.
Yeah.
And so when this was discovered, then people realized that, aha, so we need axioms for set theory. We cannot just have this universal axiom that everything is a set. We need to be more careful with that.
Mhm.
And so basically the axioms will be giving us permission what kind of sets are allowed to exist. Now that we know it's not true that everything can exist, that only certain things will exist, and so the axioms will give us certain permissions which ones do exist.
And also, I think we need to, when we choose these or construct or consider these axioms, they need to be chosen carefully such that such a problem will not arise out of these set of axioms.
Yeah, but you see, now there is no way to prove that.
Yes, again, because of this
To
incompleteness.
prove that, you need to use set theory, or it's beginning. So
Right.
it is possible that in some future, somebody will say, okay, I found a contradiction in the axiom, then we have to change them. But so far, all the science seems to work. All the science that relies on mathematics seems to work, at least as far as it relies on mathematics. So if there is a contradiction in these axioms, maybe it will mean that there is a contradiction in the universe itself, which will be a very interesting phenomenon.
Absolutely.
And so we then come to kind of making a list of such axioms, and here are some examples. So we dismiss the comprehension axiom, but maybe if anyone in the audience wants to ask some questions, because this
Yes, this is a nice
concept
time.
of non-existence of Y and hence comprehension axiom failing is an important concept. It's worth pausing on it for a few moments if there are any questions from the audience.
I don't see any questions at the moment, Zurab, but let me encourage again the participants to use the Q&A or raise their hand, and we will sort it out as soon as they react.
So no questions means that we're all happy with dismissing this.
I'm sure.
Okay, so not every collection of sets is a set, and now, as I said before, we will introduce some axioms which will tell us that certain collections still must be sets. And the first one is is about the empty set. So this thing, a collection with no objects in it, must be a set. So in my universe, I must be able to find something which later we will denote with this notation that does not have any elements in it. So the empty collection does exist as a set.
And just now we have noticed it is going to be very crucial to be included.
Yes, it will be kind of starting point of, this is also the axiom that ensures that at least something exists in the universe.
Yes, although it's empty.
Yeah, this is called the empty set axiom. And
I think there is a question here. Can you construct a matrix from those set? Which set?
we will construct matrices. We can construct matrices out of relations between sets. That will come not today, but in the future.
Next one, yeah.
Yeah. Relations between sets are very important concepts which generalize functions between sets. So thanks for asking that question. We'll come back to your question at a later stage. So the empty set axiom, as we stated now, then for instance, we have the so-called power set axiom. This is something very interesting. So I could take the set X, and I could take, okay, first I need to introduce notation. So if I have two sets X and Y, I will say that X is a subset of Y to mean that everything that's an element of X is also an element of Y.
Right.
So it means that every element of X is also an element of Y. On the picture, this would mean that if I've got X and Y here, if X decomposes into elements, and its decomposition is, let's say, consists of 5 of them, then Y must decompose into elements which includes those 5, but maybe more. The possibility of X and Y being equal to each other is also allowed here. It doesn't have to be strictly bigger. Y doesn't have to be strictly bigger than X. It could also be equal to X.
I think we mentioned a little bit before that one that two sets are equal if they have the same elements.
Yeah. So if there is no extra part, this would make Y equals X by that other axiom that we mentioned.
Yes.
Yeah. Now the power set axiom states that for any set X, this collection of all S's that are subsets of X must be a set. So if I know that,
one natural question. One natural question one can ask: what is the connection between this empty set and any arbitrary set? I mean, is an empty set will be in this collection always true?
Okay, so let's begin a bit of computation here.
Mm-hmm.
Let me first introduce notation. So this set, whose elements are the subsets of the given set X, is called the power set of X. It's denoted like this. And let's compute now power set of the empty set.
Right.
So our first computation in set theory. So what is the power set of the empty set? Okay.
But there is nobody there.
That's an easy question.
Hmm.
Sorry?
There is nobody there.
there are, as you see, there are no elements in the empty set, sure.
Right.
But now we're not looking for elements, we're looking for subsets. This is called
Subsets.
subset, this expression. We say that X is a subset of Y, right? When every element of X is an element of Y. So let's write this down as well. So maybe we can ask this question to participants to give their possible answers in the chat, if the chat is allowed. The question is to list all possible elements of this set. So let me remind you that this is the set of all the S's that are subsets of the empty set. And while participants are busy writing that up, I want to answer a question that just came through on question answer area.
Yes.
Is the empty set different from a set containing the empty set? Okay, so this question actually takes us back to the picture I made here. So
maybe that is Zurab, maybe the answer of this question is part of the question what you just asked.
I know, that's why I moved to a different picture so that I don't make it so obvious. So, this is the empty set. It's an object which, as you said, Amartya, there are no arrows into it.
Mm-hmm.
This is the set with empty set being the only element, and this one does have an arrow going into it. So you see that these two are different from each other because this one has no arrow going into it, and this one does. So they have different properties, so they can't be the same object.
Right.
So indeed, yes, empty set is different from a set containing the empty set.
Okay, so far no answer of our questions here. Oh, no answered. No, this is done. Yeah, no answer yet.
So we want to make a list here of all possible. Okay, maybe we write a bit more. So we introduced this relationship, right? So we're now looking for this relationship to hold for Y in the case when Y is the empty set. So we're looking for those sets which satisfy the fact that every element of S is also an element of the empty set, right?
Yes.
As soon as I find such S, I'm going to put it down here. And then if I find more such S, I'm going to put more things. So who can anyone maybe find for us a set S that has the feature that every element of S is also element of the empty set? I think nobody's answering because everybody knows the answer and they want to give others a chance who don't know to try to answer.
Yeah. So maybe if you know the answer, even now you can tell the answer.
So I'm going to be very rude and ask directly to Ilya. Okay, that didn't work. And the chat is disabled. So
there is an answer probably. Chat is disabled.
Is it possible to enable chat, Francesco? Is it too difficult to do that?
It seems to work on my side. Did you see that test chat that I sent you?
Yes.
Yeah, no, it seems to work on my side. I'm not sure why.
Maybe Francesco, it is active for the
panelists,
panelists only.
No,
not for the others.
Everyone.
But answers can also be posted as a question in the question and answer block.
Yeah.
Yes,
There's also Q&A. But the chat seems to work.
So if you have an answer of this question, what Zurab asked you, please write it on this Q&A sections if the chat is not working on your side. Yes. So
okay,
chat Davis gives an answer.
We have now two answers. I don't understand the second one, but the first one says that S equals the set whose only element is the empty set. And I want to explain why this is not correct. So why isn't it correct that this thing is a subset of the empty set? Well, because empty set has no elements. This has one element. If this was a subset of the empty set, then every element of the left-hand side must have been an element of the right-hand side. The left-hand side has one element.
Whereas the right-hand side,
so
nothing.
that must be element of the right-hand side, but the right-hand side has no elements.
Right.
So this cannot hold. So unfortunately, this S doesn't qualify. Do we have any other S that can qualify? Is it possible to name an S? We will maybe try to put something here so that everything we put here is an element of the empty set. And I think by this time, the question became quite trivial, right? Because the empty set does not have any elements, there's nothing we can put here. As soon as we put some elements in here, there will no longer be, there will never be elements of the empty set because it doesn't have any elements.
So
and
Nicholas gave that answer.
Oh, already,
We have
okay,
that
did you
answer.
see?
Yeah.
Okay, yeah, exactly. So, so then this becomes the only option. And so our power set of this empty set turns out to be something very tiny. It's just a set having just the empty set in it. And we can continue this computation. We can now try to compute the power set of the new set we obtained. So in other words, double power set of the empty set. So let's try to do this. We already know what power set of the empty set is, so we substitute that in. And now let's try to see what subsets does this set have. Well, we can also make our life a bit easier and do it, involve a bit of geometry in answering this question. So we've got a set here whose unique element is the empty set. And the subset is basically a portion on my picture. In this case, there are two portions, the one that contains the empty set, the one that doesn't. So this set will have two subsets. Remember, I need to list them as elements of the power set. So the two subsets will be the empty set itself and the set containing the empty set. So this set has two subsets, the empty set and itself.
And the set containing, yes.
I hope this is clear. If not, please do ask questions. We can continue this computation. We can now compute triple power set. Okay, we already know what double power set is, so maybe that will simplify the computation. Now we need to compute.
Maybe we pause a little bit to get an answer from the audience, just to understand.
Let's try to list all possible subsets of, maybe each person can propose one subset of this set.
Yes,
so
that's
we
a
can
good
list
idea.
all of them, there will be then elements of the power set.
Do we have an answer? Not yet. Yes, I think there is an answer. Yes, Davis gave an answer. Okay, so empty set will be one of these elements. And then this whole set should be one another element.
I think two have been named, two possible subsets of this set.
Right.
So why are they subsets? So empty set is clearly subset of that thing. Why? Because since there is nothing in here, it's vacuously true that everything in here is in there as well, right? What about this one? Is it true that every element of this set is also an element of that set? Well, yes, because there is only one element there, which is this one, and that we can find here.
But
Are
the
there
question
any
is,
other
yeah.
subsets? And
Okay,
I think
we have
another
an
answer came through.
That's true.
Good, correct, yeah. One
Yeah.
more has been proposed. It is this one. Sorry, this one.
The second bracket, yeah.
So why is this a subset of this? Why is that thing a subset of this? Well, because it is indeed true that every element of this set is an element of that set. We look at what the elements are. What is the element? It's this one, right? There's this one element there. And that element can be found here. This is where we can find it.
Can you have some more? Or should we stop?
There is always one more. It is the entire set itself. Everything is a subset of itself. We already said this before.
Right.
So we can add that. Okay, so we can go on, we can continue this process on, and eventually we will be able to build lots of interesting sets. And we were able to do this all because we had the power set axiom, which tells us that whenever I've already constructed a set X, I can always construct the power set of it. So thanks to that axiom, well, first of all, thanks to the empty set axiom, we know that the empty set exists in our universe. And then, thanks to the power set axiom, power set of the empty set must be in our universe. Then applying the axiom again, its power set must be in the universe. Then applying again, its power set must be, and so on. And this way, with the power set axiom, we are able to, in fact, have as many sets as natural numbers. So already our universe becomes infinite.
Infinity, yes.
The other axioms of set theory are, will have a similar use. They will allow us to build sets out of the
New
ones we
sets,
already have built. Yeah. Maybe one other axiom that is worth mentioning already in this first session is the following. This is called pairing. So for any two sets, even if they're equal to each other, let's say A and B, maybe we should use capital letters for now. This collection is a set. I mean, it's something very basic. It just tells you that whenever you have two sets A and B, you can always put them in a group. That group must always be a third set. That is written this way.
Can we do this for infinite collection, like instead of two?
Not yet. Not yet. So far, we can
yet.
only do it for two. But the case of two includes the possibility of them being equal. So in particular, we could apply this in the case when A and B are equal, and then we will get the possibility of constructing this for any set A. Because when A and B are equal, then it's the same element. And so this notation, which lists A and B, now becomes just the notation that's just A.
Of one of them, yes. Okay.
Now, of course, with the power sets, you see, we can only, just with the power set, the empty set, we can only construct sets whose number of elements is a power of 2. As you notice here, the number of elements here is 2 to the power 0, here is 2 to the power 1, here is 2 to the power 2, and so on, 2 to the power 3. Nope, sorry, I made
2
a
to the
mistake
power 1,
counting.
yeah.
the power 1. No, this is 2 to the power 0, right?
Yes, because that is empty. Yes.
Yes. Empty set is not a power set of anything.
Right.
So the number of elements here is 0. Then we have 2 to the power 0. Then we have 2 to the power 1. 2 to the power 2.
2.
That's
And
4
so on.
elements, and so on. So in general, just using the power set axiom, we would only be able to get sets whose number of elements is a power of 2. But we want more sets than just these kinds of sets.
These kinds of ways, yes. And these pairing axioms give that opportunity.
Yeah, because now we can
Yeah.
pair two things together. It will still give sets with 2 elements in it, but in combination with some of the other axioms introduced later, we will then be able to get sets which have arbitrary number of finite number of elements, and also infinite later on. So one could go into details of axiomatics and list more axioms. I don't think we should do it right now. Maybe when we will need those axioms in the future lectures, we can come back to them. I do want to copy-paste a link for those who would like to look at some of the axioms. It's a link to my lecture notes that I sometimes use for this material. But otherwise, I would stop the discussion on axioms here. Maybe you could make a suggestion, Amartya, what we could still discuss. We're already approaching the end of our session. And also the audience could ask questions if they have so far, while I prepare my link.